And we will be talking about neural architecture search now, and it is basically the art, like automating the art of AI model design. So what we have this term called architecture engineering in the deep learning. So when we started back in when the deep learning era started, we had these AlexNet and these new architectures, VGG19, VGG16. Then we had these ResNets, then DenseNets, and all of these convolutional neural networks. They were like designed by human beings. They had like tried empirically trying to like combine different kinds of layers in a different ways. So that's how these different kind of models came into being. So the design of these neural networks, convolutional networks, and different kinds of other networks, this was called the architecture engineering. So this process that we had, this was like done by humans, and it was slow and time-consuming process. It was expensive in the sense that not only you wasted time on it, you also have to like spend lots of compute hours on it. You had to like spend lots of electricity to train different kind of models that you didn't know like how would they perform. And it was basically on intuition. Uh, it was merely focused through like intuition and trial and error, as we said. So this is a VGG19 that we had, and this is a ResNet convolutional neural network with residual connections here. So the and when we were designing these architectures, so a human had this question that how many layers do we need to have in our architecture? What kind of kernel should I use in my convolutional neural network? Should it be 3 by 3 per or 5 by 5 or 7 by 7? So as an example, let me give you when in 2012 AlexNet came, it was using like a really large kernel, 7 by 7. But in layer iterations, in layer these VGG19 and residents, most of them used 3 by 3 kernels in their convolutional neural networks. So that was a shift from larger kernels to smaller kernels. And also, how many channels or number of filters do we use at each point in the deep neural network that we have? So the performance of these models is limited by human imagination and time. So the solution for this is a new field called the neural architecture search, and it is the art of using AI itself to build better AI models, using AI to improve AI. So formally, if we want to define it, so NAS automates the process of designing a neural network, and it does this by searching through a space of possible architectures to find one that optimizes a specific goal. And this goal could vary depending upon the situation. If we are achieving to match the highest accuracy, to reach the highest accuracy, we can do that. But in some places, we are constrained by computation. We'll talk about flops, we talk about max, multiply equivalents. We also talk about number of parameters in that case, or the storage, memory storage that we have. So in that case, we want to also have those constraints and as well as maximize the accuracy as well. So in this case, this is this is neural architecture search. So we have like three main components of neural architecture search that forms the building blocks of neural architecture search. So the first thing is search space, right? So as we defined, like we have, when we are trying to build, for example, a convolutional neural network before transformers, this was the most popular kind of deep learning models, the CNNs. So if we are talking about CNNs, what kind of options do we have when we are trying to build a new CNN? We have the kernel size, we have the depth of the deep learning model, as well as we have width of this deep learning model at certain places. By width, we mean the number of channels or the number of filters that we have. So these are the three main things. And also, how do you connect different layers with each other? That was also one thing that inception models, they had like different layers connected to different points. So we have these operations, what kind of layers are allowed and what kind of connections are allowed. So we will talk about the search space here is, okay, with these components, the kernel size, the channel number, the depth of the convolutional neural network, and these connections. So this forms, a search space. So if we have like different values for different components, what kind of a model do we get? So for each of these values, so we have like 4 values, 4 aspects, 4 directions. For each of these directions, if we select one type of, entity, like I choose to use a 5 by 5 kernel instead of 3 by 3 kernel. I choose 80 layers compared to like 50 layers. I choose a channel size, like really huge channel size for each of the part of my network. Then, you can form like millions and even sort of billions of models. It's up to your imagination what kind of models can you form with these options. So the obvious approach to find a search space in this case is let's find the blueprint for the entire network. So we have this global search space, and global search space is like, it's expensive. So it is up to your only imagination, and it can blow up. If we are talking about all of these options, this can become a combinatorial explosion, and it can like be an astronomical number, and it's like 10 raised to power 60 possibilities or even more. So you can like, there are 60s used in there. So you can say that there are these 10 raised to power 60 models that you can make. So how do we simplify the search space? So we have to decide a specific search space, a constrained search space within which we can find our models, right? So we have like 4 or 3 things that we can change, right? And we have to like search a good model within this space by changing these 3 things that we have. So the first search space that we will talk about is basically is a cell-based system. And this was like proposed in NASnet, a paper from 2017. So instead of designing an entire skyscraper, let's design one perfect Lego brick, which we call the cell, and then stack them. So what they suggest is that, okay, initially, instead of like building the whole network at once, why not like, okay, we first try to create small blocks, and based on the blocks, we use these blocks, okay, by connecting them repeatedly and form a network from those small blocks. So it like simplified the problem a lot. So how does it work? So we have a search algorithm, and it only focuses on finding this small cell. So for example, if we have like if we have an option to select only few convolution layers and few connection types. So since our search space is constrained, so we can like build these small cells in this case, and then we can use these small cells to like make bigger models. So this is obviously a much smaller and more manageable search problem. So they had these 2 types of cells. One was the normal cell and one was the reduction cell. And this was their network. So initially so this is the network. This has like multiple layers. So initially they had a 3 by 3 separate convolution layer. Then they have a series of reduction and normal cells. So this normal cell is basically a cell with a parallel number of these convolution layers, and parallel number of convolution layers, and they are like added and then concatenated, and it goes to the second block in this case. And the reduction layer is also a combination of these different kernel sizes. So the difference between the normal and reduction cell is basically that this has a stride of 2. It decreases the feature map compared to the normal cell. The normal cell does not decrease the feature map. So this idea of reducing this feature map in convolutional neural network is that as we proceed towards the end of the convolutional neural network, the size of the feature map decreases, but the number of channels increase. So that is also that happens in almost all the convolutional neural networks. So this reduction layer basically reduces the feature map and increases the number of channels when it's moving towards the end of the neural network. So this normal cell and reduction cell was found using neural architecture search, these two cells. So they said, okay, we found these two cells, and using these two cells, we formed this neural network. And this is what we propose in this case. So this is a much smarter way, they said. Okay, and how do they find that? Okay, they use a recurrent neural network, LSTM. You can also use LSTM in this case, but they use a normal recurrent neural network in this case to generate the candidate cells. So what they do is that they first find two inputs. Like the inputs could be like from previous layers. Then they select two input transformation operations. So any of these two operations could be selected: convolutional, pooling, identity, and and then they select a method to how to combine them. So we can see the process here, right? Uh, Here you can see that we have the recurrent neural network. So we have these to inputs here that are coming, and we select one hidden state, and then we have two hidden states. So they can like select these hidden states from the previous outputs of the previous layers or previous blocks. And then once the the inputs are selected, then they select two operations in this case. Okay, which operation do we need to select in this case? Either it could be 3x3 convolution layer, 5x5, 7x7, depending on what they need. Then the second operation, and then, okay, how do we combine them? So using this operation, they generate like this type of one cell. So they have hidden layer A, hidden layer B, and then they have these two operations that was predicted using RNN, and then this add operation was predicted here. And using this add operation, they create a new hidden layer. So in this way, they are like creating new hidden layers that could be used in further layers to like create more these types of operations. So yeah, so assuming that we have these two candidate inputs, M candidate operations to transform the input. So if we have like M operations like 3x3 kernel, 5x kernel concatenation and stuff like that, and we have these N potential operations to combine the hidden states, like concatenation, addition. This could be like the combining state operations. What is the size of the search space in NASnet if we have B layers? So if we have B such kind of layers, so this is the way that we do it. So 2x2, we have these candidates. Then M by M, we have these M candidate operations in this case. And then N, we have the type of potential connection operations. So overall, it ranges to this number, and it could like if we have M equals to 5, the candidate operations that we have, and N equals to 2, the number of inputs that we are getting is 2. So this input is basically, when we are talking about 2, it could be either the input from the last layer or the input from the layer before that. So we are backtracking two inputs basically here. So if we are talking about here, so at this stage, for example, if I'm talking about, we can either take input this from this part or from this part. So this kind of mimics a ResNet type of architecture here. So yeah, so you can see that in this search space, we have like 3 multiplied by 10 raised to power 11 candidates in the oral design space in this case. And they train this using reinforcement learning. They get these good architectures, these cells using reinforcement learning. They use this RNN in a reinforcement learning setup, and using that reinforcement learning, they try to find the best cells that would give them the best accuracy. And this takes a lot of time. You have to select best cells and then train them and check what kind of accuracy do you get, and then repeat the process, and it was like that. And it took a lot of time. And at that time, like these neural architecture search was actually really, really expensive. So, this was one example of how we can do that, this neural architecture search. But then there is a smarter way of doing that, right? That is called the supernet approach, and we have this supernet space. Okay, so the problem with cell-based search was that, okay, even with cells, the NAS net loop sample, they used to sample a cell, make a network based using that cell, and then, okay, get reward, train them, and see the accuracy, what kind of accuracy these get. So you see, this is a reinforcement learning process. They use reinforcement learning here, and this was like extremely slow. So you still have to train thousands of individual child networks from scratch, which was the main bottleneck. Then we have this another idea that is called the supernet or one-shot idea. Okay, what about what if we only train this one really big network that contains all the smaller networks? So we have this big network, we train it only once, and then, okay, whenever we need a small network, we just take that part of the network and then use it directly in our edge devices. So this giant network is going to be called the supernet. So so the main idea of this is to like decouple the training from the search, right? So we train only once this big model. Once we have trained this, then we can like search for smaller models within that big supernet, and it won't cost us that much. So step one is to train this giant supernet once. The trick is to train all possible paths, or in other words, we can call them subnetworks at the same time by sharing weights. This is although the slow part, but we have to only do it once. The second step.
Sorry.
Yes.
You say all possible paths, or all possible combinations of these different blocks.
Yeah.
Won't that be a combinatorial explosion in itself? Shouldn't this be like 10 to the 60 large, or the numbers you showed?
That is a good question. So basically, when we are selecting a supernet, right? So it is a model in itself. So we are like trying to say we have a big castle, and now this castle has like lots of rooms, but this castle itself is still limited. One is this, so we have a model, but it still is limited. Even then, we have like 10 raised to power 15 to 10 raised to power 16 number of models. It's not 10 raised to power 60, but it's like still constricted. Even then, we need a better, smarter idea way to train the supernet. We cannot like randomly take different subnets and train them. So there is a method called progressive shrinking. So starting from the biggest supernet, we start to like sample smaller and smaller models and then train them one by one. And that's how we train all the paths. And this is like a smarter way to train all these models. So yeah, that's so there are two things. Once the search space is restricted, the second thing is the training is done in a smarter way, so that almost all the paths can be like trained in a better way. So that's how it is done. Thank you. Okay, so if anyone has questions, yeah, please do ask. Let's make this more interactive. Okay. So yeah, so once this giant supernet is trained, then we perform the search step, which costs little compared to training the whole model again, and we take this subnet and then use for this. And this searching this subnet is also like that there is a way of how do we search these subnets. So this is the idea. We have this trained supernet, and we just sample these subnets and like use it for different tasks. Okay. So in this space, we have like, what kind of options do we get to change in this space? What kind of dimensions do we have in this case? So the first dimension that we would talk about is, the depth of the, our depth of the subnet. So if we have this big supernet, so we want to like, take this chunk of subnet from this big supernet, what kind of variations can we have in this subnet? So when we talk about subnet, it is part of the bigger supernet. So subnet is a small part. So we can have like different size of the subnets. It can be maximum, it can be minimum, and it can be somewhere in between. So we have the main supernet that we have is in different stages. I'm sorry. Yes. So we have these in our SuperNet that we have. Let me get the pointer. I think that last. Yeah. So we have these different stages in our SuperNet. This is the input stem of the SuperNet, and this is the head of the SuperNet. Head is responsible for classification, and input stem is basically preparing the image initially for the rest of the processing to be done. So our SuperNet has four stages. The standard SuperNet that was used in this paper. So we want to see that, okay, how many blocks can we use in each stage? So these are the, possible numbers that we can have in each of the stage. It could be, it depends upon our implementation, what kind of what number of blocks do we select in this case, right? So different stage can have different blocks, but this number of stages are fixed. It is 4, but within each stage, we can have different number of blocks. It could be 2, 3, 4, 5, depending on what kind of setting do you select in this case, right? So depth was one dimension, right? And second dimension that we have is the, resolution dimension. So what can be the input resolution in this case of the image? When we are talking about, image classification, we are talking about the image classification task in this case as well. So this could be like, the image could be like a HD resolution image, a smaller image, 60 by 60, 28 by 28 in case of MNIST. But here they're like 224 by 224. That was like ImageNet resolution. So what would be the ideal image resolution in this case? That is one dimension. The third dimension in this case would be, okay, what kind of width can we use? By width, we mean the number of channels in different stages, right? What kind of number of channels can we have in different stages? Stage 1, 2, 3, and 4. And the fourth dimension is the kernel size. So the kernel size here could be like 3 by 3, 5 by 5, and 7 by 7 in different, stages or layers in this case. So as the answer to your question, you can see that this search space is really restricted compared to the search space that we discussed in the before. It's like not, expensive as before we talked about. So they have limited this. And once this, so this we talked about the search space, 4 dimensions that we talked about of the SuperNet search space. And then, so now we talk about how do we design this search space? Okay, I just gave you an example of this search space. This was like from a really popular paper called, Once for All, Train Once Network and Specialize it for Efficient Deployment, like really popular paper in 2020. And so this, I gave you an example of the search space that does it in a smart way. But how, so if we want to design our own search space, right? We want to do it in a separate manner, like we want to create our own SuperNet. So what kind of search space would we want for our own task? So that is called designing the search space. How do we design this search space? They chose their own options, but we can also choose our own option in this case. So in this case, the search space for TinyML memory is really important when we are talking about these very small edge devices. We consider about latency constraints, energy constraints as well. So if we are talking about a mobile phone, we do not have that much energy and latency, energy constraint at least. But when we are talking about these very small microcontrollers, then we have to consider the latency and energy constraints because we are really limited on battery as well as the memory. So in this case, as you see, if we talk about this cloud AI, we have these really large GPUs that are at that time had 16 GB, but now it could go from 80 GB and even above that. Then we have these mobile AI having this 4 GB and this memory could be 4 GB and the storage could be 64 GB. Then we have this tiny, very STM32 type models that has 320 kilobytes of memory and 1 MB storage. And the gap between these edge devices and these models that we have, ResNet 50, MobileNet V2, and MobileNet V2, this is the quantized version of this MobileNet V2. The gap is really huge in this case if you look at it, right? So we have to have these. We have to create such subspaces that give us really small models. And why do we need to create these subspaces? we have to constrain the search space to an area so that whenever we sample a subnet, we get a model that is deployable on our microcontrollers, right? So consider this whole world as a search space, and we want to only focus on that area that can give us like really, really small models, but they're accurate ones, right? And within that, we need to find the accurate ones. So we will use neural architecture search to find the accurate models within that search space. Okay, so now we talked about search space. So if you have any questions, you can ask. Then we will proceed towards the search strategy. Once we have defined our search space, as we did for our SuperNet there, that was called once for all, that paper. So as we did for our once for all paper, we designed a search space there. So how do we find these subnets in this case? So how to explore the search space for a suitable model? So if we have our search space, which is obviously massive, how do we find the best architectures without like without finding accuracies for all of them? So we have these examples that are being used in different works. So we have this grid search, random search, reinforcement learning, gradient descent, and evolutionary search. Let's talk about them one by one. So initially we had this grid search. This is like a traditional way of hyperparameter optimization. So for example, if we are talking about two dimensions, the resolution dimension, the image resolution dimension, the type of image that you're inputting, the resolution of the image, and the second is the width, right? What would be the number of channels or the width multipliers, channel multipliers in our, different layers or different throughout for different blocks. So if you are talking about that for a specific, neural network block, so we would get this type of, grid in this case, and we can like, okay, write their accuracies, like, okay, if we change this part, we use this resolution and this width, what kind of performance do we get? But as you can see here, this combination thing is not like really smart. This is only for, this can be like only for any specific part of the neural network, as well as this does not cover the whole neural network as well. So it's not that smart to do this. To obtain the accuracy of each candidate network, we trained them from scratch in this case. So this was the grid search. And this is like really small and really naive way of doing this and really time consuming. Then we have the random search. So instead of like doing this grid search way, we randomly like, okay, take subnets from the search space. Like if you are talking about our supernet, we take them randomly and then try to look which model performs better in this case. Then we have this reinforcement learning. And as I told you about the RNN controller that we were using in the initial that we talked about a method, this also used the reinforcement learning. So it created a cell that it used that cell in an architecture and then trained that architecture on the data set and got the accuracy. And if that accuracy would get higher, it would get a positive reward. If the accuracy get lower, it would get a negative reward. And this would process would go on. So we have the controller, neural network, recurrent neural network. It would sample an architecture then it would train that architecture. The system would train that architecture on the data set, and then it would give information back. So compute gradient of P, that they have this probability of P and scale it by R to update the controller. And this was a process of, a feedback mechanism. Then we have this gradient descent way of searching. And this is like also interesting. This was from Dot's paper, Differential Architecture Search in 2019. So represent the output at each node as a weighted sum of outputs from different angles. So what they do is that, consider, that if we have this inputs from, this layer to layer 1, layer 0 to layer 1, layer 2, and layer 3. So we can have like multiple paths from 0 to 1. It could be 3 by 3 layer, 5 by 5 layer, 7 by 7 layer, like kernel sizes. And it could also be that we do not go from 0 to 1, we just go from 0 to 2 and then 2 to 3. Then we have like different kinds of paths here, right? You can see here. So in neural networks, what we do is that when we get an output, and we get the loss, and based on the loss, we take the derivative of the weights and then, okay, back propagate. In this case, they also make these the weights of these connections also differentiable. They add this to the loss, and based on that, they like, okay, try to find out, okay, which connections give you the best accuracy, right? And using that knowledge, they, okay, say that, okay, this is the best subnet. So initially, the 0 to 1, all of them are connected, right? All of them are connected, and all of them had like multiple types of kernels. They start training, and with time, they like, okay, try to figure out, okay, which connections are the best and which type of kernels do we need to select in this case. So that's how they choose it. So this was basically included in the entire training process. So, from input to, we have, if we are talking about 2 layers, so we have this input, this passes through different layers, and then output. And we have different weights for alpha, beta, rho, and this lambda. Then we have different weights for all of these, and these are added to, the loss function itself. These weights are added to the loss function itself, like, and they give us like, okay, what kind of, output do we get? Basically, yeah, so this is basically, they are included in the loss function, and that's how we learn the values of these weights. So then we have this evolutionary search fitness function. And this is the most commonly used, and the paper that I mentioned, Once for All, which presented the supernet idea. So you can ask the question, when I was mentioning about these different ways of searching for different models, you might have asked, like, okay, if we have a supernet that has these trained subnets within them, so how do we like, okay, search different subnets within these? How do we select the best subnet from this supernet so that it can match our constraints, memory constraints, compute constraints, as well as it gives us maximum accuracy? So in that case, we use the evolutionary search. What it does is that we sample a subnetwork in this case. We evaluate it on the data set. If it gives us good accuracy and it is within the constraints, we take it. Otherwise, we sample another subnet. But this is done in a genetic algorithm way, not in like a random process way. So we use a evolutionary search in this case, and it's like a generic, and we use a fitness function. And this fitness function could be like the accuracy, and based on accuracy and efficiency. Efficiency we mean by the constraints are the MAC constraints, the number of parameters, the storage constraints, and the accuracy is basically what to maximize the accuracy. We will get back to this evolutionary search again and explain it in detail. It's quite interesting. So we discussed about the search space. We now discussed about the search strategy, right? How do we search for these subnets or these models? The third thing is that performance estimation. Okay, how do we actually judge a subnet or an architecture quickly? Because if we talk about the performance estimation, the obvious way of like estimating a performance of an architecture is like, okay, for any proposed architecture, train it fully on the data set until it is converged, and evaluate its accuracy on a validation set. So this is like our, okay, reward or the performance estimate in this case. So what's the drawback here? The drawback is obvious. The original NAS paper trained, to 12,800 models on Cypher 10. This was basically the Zoff et al. Paper that we mentioned that used the recurrent neural network, right? So it trained like 12,800 models. So this took 22,400 GPU hours, around 2.5 GPU years. So scaling this to large data sets like ImageNet is computationally infeasible. So they did this for Cypher 10, and scaling up to ImageNet is like impossible. So we need a faster way to estimate the performance of our models. So the smarter approaches in this case would be hypernetwork-based estimation. Hypernetwork-based estimation is basically, you can say that, okay, we train a neural network for predicting the accuracy of different networks. So if we have a neural network that have like a specific kind of weights, and we input those weights to a neural network, and that network can like provide us an accuracy value that can be like a sort of a estimation of the current network that we are trying to design here. So this is basically hyper-network-based estimation. And then we have these proxy or surrogate models, weight sharing and supernet based. So this is the smarter way to do it, and the ones for all also used. So, but what do we mean by proxy and surrogate models? Let's talk about this. We'll talk about this in the next section in this case. So let's summarize this. So we talked about NAS, which automates the design of a neural network using 3 components. We have the search space, we have the search strategy, the brain that we use to like, okay, how to select these subnets or these models. And then we have the estimation, like, okay, how do we judge that? Okay, which architectures are better? So do you anyone have a question before we move to actually going into this once for all solution, OFA? Okay.
This is more of a curiosity.
Yeah, sure.
You talk about this large problem of finding the supernet or the. I was wondering if there is any research going into use some quantum data or quantum methods to do this once and for all training. Does that work with NAS? I know any such things.
I'm not familiar with this quantum domain much, and I don't know like how much of work has been done there in the neural architecture search part. So, but I think compared to that, I have seen trends like moving towards transformers for neural architecture search, and this is also like more people are more focused on that thing. Okay, if we have this big transformer and we want to deploy these transformers, smaller versions of the big transformer on smaller devices, so how can we do that? But this quantum thing, since it's not like my main field, and I haven't like looked much into this, so this could be an interesting direction to also like look into if someone is interested in it. But a good question. Okay, so now we talk about the once for all train network and specialize it for efficient deployment. This was like sort of a big, really good paper worked by the people at MIT. So the goal is to find efficient neural network search for deployment on various devices, and the main idea is to train one large network and extract smaller networks that are specialized for the deployment part, right? So we have this. Initially, we have this like, okay, the process was like this. Then before the once for all, like, okay, we have this subnet. We have this model. We train it. We check its accuracy. What kind of accuracy do we get, and what is its latency? How much time does it get to give us an output? If it is good, then we keep it. But if it's not good, then we resample another architecture and train again. And it was like really costly. But this paper, this method shows us, okay, we have this big network, we sample a subnet, and we have some proxy way of a surrogate model or proxy way of determining what would be the accuracy of this subnet. So we don't even need to like actually evaluate this model. We have a smarter way of actually predicting its accuracy, and we will talk about that. So this decouples training from search, as we said. So how does it train the supernet? So how do we train the supernet? So we talked about the dimensions that were in supernet. After supernet, we have depth, width, kernel size, and the image resolution. But how do we train it? We train it by progressive shrinking. So the once for all method basically first trains the largest model, the overall supernet on our data set, like the ImageNet, and then it slowly decreases the model size. Like if we have the big supernet, it would take a smaller version of that supernet, the subnet, and then train that one on the same data set. And in the next iteration, it would take even a smaller model and train again on the data set. And in this way, it keeps, shrinking the model as well as training it on the data set. And there is also another part in this case. They also use knowledge distillation. The supernet itself is a teacher to the smaller models, right? In the loss, they also include the supernet to train the smaller models. So this is like an intelligent way of like, okay, the supernet is a teacher to its smaller versions. So there are two things happening at the same time. So it's like really smart way to train these models. So the current model acts as a teacher for knowledge distillation from the shrink model. So and the teacher also keeps moving. Like, okay, initially it was a supernet, and then the teacher is also shrinking in this way. So if we are talking about shrinking, so we progressively prune the kernel size, pruning as Obed mentioned about. So we make these things smaller. So kernel size, depth, and resolution, we make the kernel size smaller. So initially, if it was 7 by 7, we make it 5 by 5, and then 3 by 3. If you are talking about the layers, we take the layers one by one out. So initially, if we have this full depth for a block, if you are talking about a single stage, we have these 4 layers. In this next iteration, we would like, okay, decrease this one layer, and we will have only 3 layers. And then this output would go to the next stage. But in the third iteration, we only have these 3 layers, and the output would go to the next stage. Then we have a progressive shrinking in the channel size. So we also decrease the number of channels that are used in different iterations. So yeah, so this is basically progressive shrinking, the way they train their supernet, and quite interesting way to manage this. So we have this hardware-aware specialization. So each device has its own hardware constraints that we said. So OFA customizes a subnetwork for each device, optimizing for accuracy, latency, or memory. So we need to also talk about, okay, how do we select a sub? Now, once the supernet is trained, how do we select a subnet for deployment onto our edge devices, right? How do we do that? How do we select the best supernet? Okay, we trained the supernet. So we need to maximize, for doing that, we need to maximize accuracy under a latency constraint, or maybe max constraint, or the storage size constraint. So we have to do that. And the result would be the best possible model for each hardware target. So yeah, so as I discussed before that, how do we find the subnet? So we do it in an evolutionary way, a genetic algorithm. So you can say that we have 4 dimensions, and using these 4 dimensions, we have different values for these 4 dimensions. So we have this, we initialize a population of like 100 or 200 architectures. You have to we have to search on this, genetic algorithm. I did not include those slides for a specific genetic algorithm because it is pretty standard, but I will update it in the new iterations. So, I will just briefly mention that. So a genetic algorithm is basically what happens is that we initialize a population of these subnets, like 100 or 200 subnets, by selecting values for each of the 4 dimensions that we have. And once these are selected, and we have this population, 100 or 200 population. Now we are going to like, okay, select, okay, we are going to measure like what kind of accuracy do they give us, right? And and once they are selected, okay, we know which one. So the models that are at the top, we take them and okay, do 2 things. One is the crossover. We share genes. By genes, we mean these dimensional values, and also we do mutation. We also randomly switch these, dimensional values to get new children between these top n number of models that we have. And this process repeats n number of times, and we get the final model by like repeating this process. And after some generations onwards, we call it generations because we repeat them n number of times, and we have these children's coming from the parent subnets. So after some generations, we get the top most fit models for our task, and that are like actually able to provide us best accuracy, as well as follow the constraints that we have for our edge devices. And the main thing here is that, okay, but the question here would be like, okay, if we are talking about 200 or 100 models here, subnets, how do we actually measure their accuracies? So for that, the authors, what they did was that, okay, for a specific device, right? For a specific device, what they did was that they collected a data set of accuracies as well as latencies. Okay, for example, an STM32, they like collected a data set. Okay, like on this device, this subnet would give us this latency and this accuracy, and they like collected a data set and trained a simple MLP, multi-layer per spectrum. And whenever we would get a subnet architecture into this MLP, it would give us an accuracy value as well as a latency value. So this is a little bit in depth that we talked about. So it is basically a predictor guided search. It is called a predictor guided search using an evolutionary method or a genetic method. So an upgrade of this once for all was the big NAS, scaling up the once for all idea. So problem in OFA was it uses progressive shrinking. Training in phases is still like slow. So and training is also not fair because larger subnets dominate the gradients updates while smaller one get less attention. So for the motivation for big NAS was to improve fairness and efficiency of supernet training. And the goal was to get all the subnets like performed reliably. So this extends the once for all approach with new techniques. So what they do is that they train the entire supernet in one single stage without progressive shrinking and without any external teacher. So they use this in-place knowledge distillation thing in which they say that, okay, during training, we select the largest subnet that would act as the teacher. The smaller subnets would act as the students, and both are trained together. So we discussed about, on a combination of online distillation and self-distillation. So this is the same thing. So the biggest subnet or the supernet itself is being trained while the students are also being trained. Smaller subnets are also being trained. So both are trained at the same time. And the biggest subnet or the supernet, in other words, it acts as the teacher for small students. So this makes the smaller subnets learn better representations, and it does not like need extra pre-trained model to become the teacher, because in the once for all, we had to like take the bigger subnet, train it, and then take the smaller subnet, while the bigger subnet is like being a teacher for the smaller subnet. But here, both the bigger subnet and the smaller subnet are training at the same time, while the bigger subnet is acting as the teacher itself to the smaller subnets. So this is an interesting way and a smart way to do it. So they had like these three things: in place knowledge distillation, largest subnetwork acts as a teacher for smaller ones; a sandwich rule, train largest, smallest, and random networks each iteration. So sandwich rule is another idea. Like if we want to train these supernets, we take the largest subnet, that is the supernet itself, in each iteration, the smallest subnet, as well as a few random subnets between the smallest and the largest subnet. So we take these and pass a batch of images through that and update their weights using knowledge distillation as well as the cross entropy loss. And this is a single stage training, eliminates the need for progressive shrinking. So the result is a balanced, efficient training for all subnetworks. But why this big NAS matters? Because it's improves the consistency between subnetworks and their models. Their final models ensures these subnetworks are not like neglected during training. More accurate and fair weight sharing in large scale NASes, and then the training is obviously simplified and improves deployment efficiency as well. So this is like the difference between differences between OFA and big NAS, in which case like we can say that, okay, big NAS has single stage end-to-end training, whereas the training for once for all is multi-stage progressive shrinking. Knowledge distillation, in knowledge distillation uses an external teacher model in once for all, but in big NAS, in-place distillation is used, in which the bigger model is the teacher during the training. And the training is faster in case of big NAS as well. And then we have this pre-NAS paper, the preferred one-shot learning for efficient NAS. The motivation of NAS, one-shot NAS is the motivation for this paper is that one-shot NAS, as we discussed about big NAS as well as once for all, is that it still wastes time on weak subnetworks. So why not? So in once for all and big NAS, we are still like randomly sampling subnets, right? In big NAS, which is an improved version of once for all, we sample the largest subnet, which is the supernet itself. We sample the smallest subnet, and we sample random subnets in between. So if we are sampling these random subnets could be like bad subnets, right? These could be bad networks, and we do not want to train the bad networks. So what if we only take smart networks, really good networks, instead of taking random networks and then train the supernet based on that? So this is their core motivation. This reduces training cost and search space while improving the performance. So if this is our space, the supernet space, and we only take the small models, the small ones that are like really good in performing, we only train them. And in that case, the supernet would like train much better. But how do we know that which subnets or which models are good, models would perform well? So they present like use a zero cost selector, quickly estimate promising subnetworks using lightweight metrics. So they use some metrics to like, okay, determine what kind of subnets would be better. Then they focus the supernet training only on high performing subnetworks. And once the training takes place, each subnetwork is ready for specialization after shared training. So, if we have this, if we are talking about this transformer, so they also use this transformer type of model in this case, once for all. And this is like the resources and the performance, and these are like different subnets. So what they do is that this is the surface for the subnets, and what they do is that they select only the top subnets that they would give based on the resources, that top subnets that would give you the best performance based on the resources. So they select only these subnets, train the supernet on this, and then like once the supernet is trained, they can use evolutionary search to get like these best subnets again for deployment. So this is yeah. So basically, I'm explaining it there. So I just basically wanted to the same thing here. So they select the best subnets. So these are the best subnets here. They use these to like, okay, train the models. Once the models are trained, then they can use directly use the same zero cost search to get the subnets. Because evolutionary search is not needed here, they can just use this zero cost search to get the subnets here. So you can say that the evolutionary search is also like, they can like ignore this here because they already have a search function here with which they selected the best subnets. Using those best subnets, they trained the model. And then once the model is trained, for any task, they can use this zero cost search to like, okay, select the subnet that they want. So that is how they got it. Okay. So the impact of pre-NAS on NAS and TinyML is that significant reduction in research complexity and better utilization of compute. So it eliminated the need for retraining thousands of subnetworks. So more hardware-aware model selection for TinyML devices. And with pre-NAS and OFA, we have this faster part of specialization pipeline. And this represents towards next evolution of like NAS. So it is becoming smarter day by day to like sample subnets and train these supernets. So we talked about, so let's talk about this evolution. We talked about this NASnet, where that was like basically cell-based one, and it uses reinforcement learning, and it was really costly. Then we talked about differentiable NAS that like focused on basically making these connections and kernels based on also differentiable, the weights of these connections, different connections with different layers, as well as the kernels. Make their weights differentiable so that they can also be trained. They can also be learned during training. Then we have this once for all, train once and specialize many. This is like using regressive shrinking. Then we had big NAS, single state sandwich rule, and in-place knowledge distillation. It used. Then we have pre-NAS, preferred one-shot training for efficiency, and then we have this DeepMed. So DeepMed is also something like what this method does is that it provides you a mathematical way of determining which model would perform well based on your constraints. You don't even have to like train a supernet in that case. You just need to use a mathematical formula, perform this genetic algorithm, perform a search using the genetic algorithm, And its fitness function can like provide you a good architecture for your task, and then you can train that architecture for whatever task you're working on. So one idea is to like, okay, combine these deep math ideas with OFA, and like, use this deep math as a proxy function for determining accuracies. So yeah. Thank you for listening. I hope it wasn't that much confusing. So if someone has any questions or something that I would be glad to answer. Okay, I don't think anyone has questions. So thank you so much for your time, and should we have a break, or we can start working on our next session?
We'll take maybe 30 minutes, 6 questions.
Yeah.
Simple demonstration on like
Yeah.
how all this now sums up to be deployed.
Yeah.
So,
Okay, so
5 minutes.
yes.
5 minutes.
Yeah, we can have a
So you
10
grab a
minute
coffee
break.
and-
Yeah, we can have a 10 to 15-minute break. You can just refresh up, and then Obid will show you how we deploy these models on a edge device, and we would like to show you how it in a real time. So,
Hej förresten,
Hej,
Anna.
Joakim.
Så, du var ju med även på cloud-kursen.
Ja, det var där.
Jag kände igen din
precis.
röst.
Ja, exakt.
Yeah, I think I could have